Okay, that sounds like the recording's going. Then I'll just start sharing screen to. Okay, cool. That should just be showing the PowerPoint with. That's showing just the PowerPoint, right? No speaker notes. Okay, cool. Thanks. Okay, so before I begin my presentation, I would just like to acknowledge the Gadigal people that are the traditional custodians of this land which I am delivering my webinar from, and I would also like to pay my respects to elders both past and present. Okay, so the title of my presentation is Reliable Electrical Systems. If you saw the advertising, I found this meme, thought it was quite funny because I've quite literally seen this happen before in FRC, so it's not wrong. And hopefully we'll walk out of today with some ways on how to not be in that situation. Just quickly introduce myself. My name's Dawood Ramadi. I'm a third year electrical engineering student at UNSW. I mentor multiple FIRST teams and I volunteer with FIRST as well. This year, I'm the tournament director of two tournaments here in Sydney. So if you're free on the weekend of November 29, please do sign up for our FLL event, Eastern Sydney Regional. And then that's me. Okay, now I did want to start with a disclaimer. I'm not going to purport to be some sort of authority on this topic, and a lot of it's going to be somewhat anecdotal sort of case studies and whatnot. So basically, I just want to say, don't blame me if something goes wrong. And also the advice I'm giving, in certain areas, it will be more practical, not necessarily the optimal. And you'll see what I'm talking about. So I just wanted to state that disclaimer. And then some of this advice is subject to change as time goes on, mainly having to do with it, for example, with the Robo Rio. In 2027, that's getting kicked off, and we're getting a brand new control system, which I'm looking forward to. So, as time goes on, some minor things of this presentation, might fall out of date, but the general gist should remain. So I wanted to start off with just quick show our robot from EMU Robotics this year called Perry. And also in the description of this, webinar, I said, how can we make fairly reliable electrical systems even with unimpressive robots, right? I was sort of referring to EMU's robot here, right? Nothing wrong with our robot, but, just standard run-of-the-mill. It ended up just being able to do L2, L3, but it still made it to, for the first time ever in our team's history, to regional finalists, even just being able to do two things, right? And I would like to attribute part of that to, okay, well, the electrical was fairly reliable. I think over the entire season, we had maybe two electrical issues, and one of them was human error. So having reliable electrical, even with, you don't need a Einstein level robot, it will help you significantly. And why is electrical important? I had to include one cringe equation. So no elect, pretty much no robot. And, if you have no elect, this will be you and maybe your robot. I don't know, hopefully not. But look, let's get into the agenda. So I'm covering multiple things. As Haley said, please do feel free to place questions in the chat and interrupt if you'd like. That's not a problem with me. Primarily, I'm gearing this presentation towards FRC, but if you have any questions about FTC electrical, please do ask during the Q&A. Okay, so we'll cover what brownouts are, cover CAN issues, some oddities with some specific certain components, some DS issues, so driver station issues, if you don't know what DS is, driver station, some radio issues, because there's been some newer issues coming with the new Black radio that we have starting this season, some issues having to do with transporting your robot, and then some steps to take when receiving new electrical components. So this is a general outline of my webinar. Okay, brownouts. So what is a brownout? Why do brownouts occur? And how can we tell if brownout is occurring? So these three questions I hope to answer. And then, of course, how can we mitigate those? So what is a brownout? the first thing we actually need to look at is the equivalent circuit model of a lead acid battery. So hopefully we all know that in FRC we use a lead acid battery with a nominal voltage of 12 volts. And it's a sealed lead acid battery. So that's just a type of battery chemistry. We have other types of batteries out in the world, like nickel metal hydride that we use in FTC, or what you probably are all more commonly familiar with, lithium ion batteries. But we use lead acid batteries in FRC mainly for safety. If you puncture a lead acid battery, yes, acid will spill out of it, but that's a lot easier to deal with than puncturing a lithium ion battery, and it explodes. So that's why we use them mainly. So I made this very interesting diagram here. If you know LT Spice, I just used that real quickly. And can we get a laser pointer? Here we go. So this is your battery and depicted as an ideal voltage source with nominal voltage 12 volts, right? So you're expecting when you buy a battery, you're going to get 12 volts out of it, and that's the end of it. But it's really not that simple. In what actually is the case is the voltage that you're getting out of it here, that you can see V out, that will be actually the voltage you're getting out of the battery, right? With the cables coming out of the battery, wires coming out of the battery, that's what you're getting, this V out here. There's actually this resistor, IR, internal resistance. It's not a physical resistor that's in there. It's just because a battery is an electrochemical device, and that chemical process that occurs to actually create your voltage, your potential difference, that can be modeled using a resistor. And in this case, 12M means 12 milliohms. So you can think of the battery, the voltage that you get out of it, and the actual, if you were to look inside with an equivalent circuit model, as we call it, it's a voltage source in series with a resistance. In this case, you'll see why it's 12 milliohms in a moment. Also, in case you don't know what voltage is, like I said, that means potential difference. So electrical potential difference in this case. So most of you will know what potential energy means, right? You lift a boulder up a mountain, right? And it has more potential energy the higher you get up that mountain. And when you let it down, there's kinetic energy, right? So voltage is defined as our electrical potential energy, with electricity just being the movement of electrons, and then current, represented by I, which you'll see in a moment, that's just this sort of flow rate of those electrons. And then resistance is pretty straightforward, right? Just how much resistance is a component resisting that flow of electrons. Okay. So as I said, in FRC, nominal battery voltage of 12 volts. Now, here we go. This is where we're going to actually start talking about the brownout here. So with our control device in FRC, which is called the RoboRio, it has a set brownout voltage of 6.8 volts. Basically, that means that we don't want the input voltage into our robot to drop below 6.8 volts. Otherwise, bad stuff will start happening. It's sort of an arbitrary number in this case, but I will be including many links, attached to this recording of the presentation, and one of those links will be a WPI lib doc, where you can actually read more about the brownout voltage, how that's been selected and whatnot. But we'll take 6.8 volts for right now. As I said, the nominal internal resistance is 12 milliohms. Where did I get that from? I had a data sheet, which I will share later in the presentation, from MK Batteries, which is a very standard battery supplier in FRC, and they've listed their internal resistance as 12 milliohms, so we'll go with that. And then hopefully we all know Ohm's law, which just says that the voltage is equal to the current times the resistance. So here I have my voltage, I have my I, which is my current, as we said, and we have my resistance, which is the 12 milliohms, which I've said. Now, why are we minusing 12 by 6.8? That's because voltages are relative. It's a potential, right? So we need to actually find out, okay, well, we can go from 12, which is what we have, our nominal battery voltage, down to 6.8 dropped across this 12 milliohm resistor, to find out that theoretically we could be pulling 433 amps from our battery before we drop below 6.8 volts, and we have a problem. Now, in reality, you're not going to be getting 433 amps, because if you look at the data sheet of the MK battery, for instance, it rates it at 270 volts for 5 seconds, right? And really, you might have a spike up to 433 amps, but it's not going to be longer than a second, probably in the milliseconds range. But why did I show this equation? Just so you can get an understanding of, okay, what's actually happening with the lead acid battery, and what's a little bit of the intuition for what I'm going to cover next, which is, I still haven't really covered what a brownout is. Brownout, like I said, is when we drop below this threshold voltage of, in this case, 6.8 volts, and that's due to a large amount of current, right? Because as we said with Ohm's law, V equals IR. So the more current that flows through this internal resistor, the more voltage drop we're going to have across that. And the more voltage drop we have across this internal resistor, the less voltage that will be available on our Vout at our battery terminals, right? So as we power more devices and do more things with the robot, as we begin driving, shooting, defending, whatever it is, our current flowing through is going to increase, and our voltage drop on this internal resistor will increase. Therefore, our voltage at the output of that battery will decrease. Okay, so covered what's the brownout, why does it occur? It occurs because we're pulling current from the battery, and the battery has an internal resistance, which is then dropping some voltage. Okay, great. And how can we tell this is actually happening? This whole big blobbing that I did, how do we actually know the brownout's happening? Because we want to, that's what we want to prevent, right? So hopefully we all know what RSL is, right? It's that light on the bright light on a robot, the orange one, robot signal or safety light, depending who you ask. And it's solid when we're disabled, and it's blinking when we're enabled, right? And it's blinking actually at a certain frequency. I think it's like 2 hertz or something. I don't remember. You can find it in the game manual. And if you're browning out, that blink will begin to be sporadic. Maybe it'll stay on longer than it should. Maybe it'll blink more than it should, depending on what's happening with the robot. You'll notice that you're browning out just by the RSL, by looking at that. So I've been able to see and tell someone on the live stream, for instance, I was just watching a live stream, I saw the robot, and I see the RSL is going weird, and I already knew there was a brownout. Didn't even have to be there in person, just looked on the live stream. The other way is the driver station. And I think this year, from what I remember, is that the driver station actually, with the 2025 update, now when you brown out, the whole bottom of your driver station screen like turns orange to show, hey, you're browning out here. So those are the two sort of ways you can tell. And if you're driving, you'll tell, right? The robot's gonna begin to become unresponsive. It's gonna get sort of jerky, right? So you might be trying to drive in one direction and it's going forward, stopping, forward, stopping, forward, stop. This is a problem, of course, right? We want smooth driving. We don't want, to be jerking around when we're driving, when we're trying to defend, even when we're trying to shoot, right? And for example, in a game like, I don't know, Charged Up, for instance, right, where you have protected zones, you don't want to be spazzing out while you're in a protected zone and you get stuck there. Bad thing to happen. So how do we actually, mitigate these brownouts? Because we don't want it to happen. Easiest way, and this is what I was talking about, where it's not optimal advice, but it will work, right? And I've seen it work, is setting an aggressive current limit, right? And some people will say, well, look, you're putting, you're leaving so much performance on the table if you're, current limiting your motors. Well, here's the thing. Do you want to be able to drive nicely, even if it's a bit slower, or do you want to get your maximum performance and you're not moving at all, right? So that's sort of the trade-off here. And let's say you're in the heat of the moment, right, at a competition or something like that. This is like one line of code to push. It's quite quick, as opposed to the next couple of mitigations we'll go over, which can take a lot longer, right? So if we set, for instance, on a Kraken motor, a supply current limit of 40 amps, well, now the motor controller will not allow the motor to draw more than 40 amps from the battery. that's a good thing because, like we said, less current flowing, less voltage drop we're going to have, and hopefully we'll stay above that 6.8 volts and not brown out. Right? So this is a very quick thing you can do. Personally, at EMU, we don't typically go above 40 amps. Many teams run 80 amps, which you can do. I'm not saying you can't do, but then this is when the next things come into play. So one, you need to check your battery and power leads and make sure that they're actually solid. Many times I've seen either the battery, the leads that connect directly to the battery, or your circuit breaker leads, or anything in between. If they're loose, then that's going to add resistance into your power path. And we don't want more resistance, we want less. So think about it, if it's loose, it's worse of a connection. So it's not gonna, our electricity is not gonna flow as well. So that's a fairly quick thing to check. Okay, are my battery leads good? They're tight, making a good connection. Are my power leads on my circuit breaker, for instance, are they good? Are they making a good connection? And in the links that I'll provide, I believe one of them does show, there's actually some interesting posts on Chief Delphi about how to best wire your battery, the connection between the lead and the battery terminal, because many times, over the course of a competition, especially due to the vibration, that joint begins to loosen up, and then the battery lead begins to be able to rotate, which is not what you want. And third thing is, now when we're getting into, okay, a lot more pre-planning is going to be needed and a lot more consideration is going to be needed, and this is not something you are going to be able to do on the fly at competition, is considering lower gauge wire. Now, if anyone's familiar with AWG, American Wire Gauge, the lower the number is, the thicker the wire is. So it's a little bit counterintuitive sometimes for some people, but basically a 6-gauge wire is thinner than a 4-gauge wire. And if you've taken physics, I don't know what year they would cover it here, but there's a formula that the resistivity of a wire is inversely proportional to its cross-sectional area. So basically, what does that mean? The thicker wire we have, the less resistance it's going to have. So if we use a lower gauge wire, it will have less resistance, which is what we want. So for instance, we can install on our battery wiring, we can go down from the typical 6-gauge that they include in the kit of parts with the SP50 Anderson power pole connector. That's the red one. And we can actually upgrade that to 4-gauge with a SP120, which is the blue Anderson power pole connector. And that 6 to 4 gauge will reduce your internal resistance caused by your wires on at least that battery part. One caveat to mention is most teams in Australia, they're using SP50 connectors, the red ones. So that's something you want to keep in mind, because if you're at comp and you have, for example, the SP120, which is larger, make sure you bring an adapter for that, because let's say something happens, you need to borrow something from another team. If they're not using SP120, then you might be out of luck if you don't bring your own adapter. Other places to use lower gauge wire, most of the power wires on FRC robots, typically teams are using 12 gauge. For motors like Krakens, you can use 10 gauge and you'll save, once again, you'll save some resistance there. And considering the Krakens pull quite a lot of current, especially if you're running them either without a current limit or 80 amps, you can get a bit of savings through there as well. Okay, another thing, if you check your battery connections, right, and you see that the cable is breaking near the lug where it's actually connecting, right, this is time for you to either recrimp that cable or just replace it outright. So these are 3 things you can do to mitigate brownout. The other thing is just some really quick things. Are you swapping batteries every match? Are you swapping a fresh battery every match? I've seen times where we swap the battery, right? And I'm saying many different teams that I've seen and experienced, swap a battery, and it's the same battery. It ends up being maybe a battery that just came off or something like that, not a fresh battery that's been on charge. So we want to make sure we're swapping out our old battery with a new battery that just came off the charger that it was indicating fully charged, right? And you can use a tool like the Battery Beak to actually test your state of charge and see, okay, is this battery good? Also, something you should read on the Battery Beak manual. 100% state of charge on the battery beak is not actually 100%. It's either 120 or 130, if I remember correctly. So read the battery beak manual if you're using a battery beak, and actually you'll find out that you should actually be reading 120 to 130% state of charge for that battery to be competition ready. Additionally, the battery beak will give you a rough estimate of your internal resistance of that battery. I'll go over how we actually can measure that later if we have time. Of course, we want to use batteries during our competition matches that have less internal resistance, not more. And over time, the internal resistance of the battery will increase because of the chemical reaction going on. There's a really good battery video I will link if we have time. It's only about a minute and a half. I'll play it, but we'll see. Okay, power disconnections. This one I didn't really put into the agenda, but sometimes, for example, in 2023, they had the cable protector on the field. And many robots that year suffered the fate of they would drive on top of that cable connector. There's a bit of a jolt that happens to your robot, and their robot would get turned off. And if your robot loses power, especially either the Rio or the radio, they take forever to reboot. Minimum 60 seconds, which is almost half the match, right? So we don't want our power to be disconnecting. It's really a bad thing. So if your team is using a ferrule, you should ensure the ferrule is large enough for the connector it's going into. Because if you're using too small of a ferrule, that little jolt can actually temporarily disconnect it just long enough to shut you down and then bring you right back up, which can be quite annoying. If you're using PWM cables, most of us are using CAN, but sometimes you use PWM cables for sensors, what have you. Make sure you zip tying those together. This is FTC relevant as well, right? Have either a zip tie, maybe a 3D print, to actually make sure those stay together. If you're using Anderson power pole connectors, this is very commonly used by FRC teams. They have this thing, and I've seen this happen recently. I saw this, and it's happened many times, where they look to be connected. It looks all good. You look at it surface, level, and it looks like it's connected, and it's not connected. You can actually push it in more, depending on the quality of the crimp. Different failure modes can happen, but it'll look by a visual inspection connected, and then you tap it, and then you find out, okay, well, it wasn't actually connected. I tapped it and it became connected, right? So do a pull test on your Anderson when you fabricate them. When it's separate, pull on that Anderson connector and make sure it's actually connected to your wire. But also you might try unplugging, replugging the Anderson. And you might even try an electrical test, right? Get your multimeter out with the robot off, measure continuity, and see, okay, between both ends of my connection, do I actually have continuity? And for instance, you can actually measure that resistance once again. If you're getting, let's say, maybe 100 ohms, technically there's a connection there, but it's a pretty bad connection if there's 100 ohms of resistance on there. So Andersons can provide some trouble if you don't do the right things with them. Other than that, they're pretty good. Protect your main breaker. There's a 3D print on Thingiverse or on Chief Delphi or something, 3D print that you can print out for your main breaker to put it on top. I remember watching this match in one of the Turkish regionals, I think, during 2022, where you had over the bumper intakes. One team accidentally goes boop and shuts off another robot for the rest of the match because their main breaker was accessible enough that this other robot's over the bumper intake was able to shut them down. So if you had a cover on there, it wouldn't have been able to hit that and shut it down. There's also been, game pieces that come. Maybe a coral hits your circuit breaker and shuts it off, right? So you can prevent that by printing a cover. That way the button's still accessible, but something like a game piece or another robot won't actually accidentally disable it. Because, once that main breaker is turned off on the field, it's not getting turned on until the next match. Another thing about the we'll move on for now. If you're moving, this one's not about power. This was about when you should disconnect the power, sort of. If you're removing a radio or Rio, let's say you need to swap a radio out or something, or you need to go program your radio, something like that, pull the fuse on the other end where it connects to the PDP or your PDH or whatever. That way, if you accidentally connect the red and the black wires, you don't end up blowing the fuse because the fuse has been pulled out and there's no actual voltage across the red and the black. In 2022, I personally did that when removing, power connection to the VRM and blew a fuse, if I remember correctly. So it happens to the best of us, so just pull that fuse. It doesn't take that long. Okay, so that's brownout plus power disconnection. A lot of the causes of unreliable electrical systems on FRC robots that I've seen happen many, many times. Now we'll move into the second largest thing, or I would say probably CAN issues are just about the same as browning out and power disconnections. We have CAN issues. CAN bus is probably one of the, in my experience, one of the parts of the electrical, FRC scene that students have the most trouble understanding. So, and I don't blame them. Can be a bit tricky at times, but it's actually not that bad. So one issue is identical CAN IDs. So when you, let's say you get brand new motors, right? They are all coming out of the factory with no CAN ID. And since they all have no CAN ID, they're all technically identical CAN IDs. So when you all wire them up, it's sort of as if we all had the same name. Then we wouldn't know who we're talking about, right? So same with these motors. If they don't have different CAN IDs, we're not going to be able to address them and do what we want with them. Now with CTRE devices, usually Phoenix Tuner is able to resolve the CAN IDs if you set them one by one. So basically it will show one motor and it'll say like 14 conflicting CAN IDs or whatever. And as you begin to set, you just randomly set a CAN ID, it will then move that motor outside, and then you can continue to set CAN IDs iteratively and go that way. Rev products don't have that from my experience. So the best way to do that is one by one. You hook up, for example, to the SparkMax directly with USB-C to your laptop with the Rev hardware client, and you set the CAN ID and label it at that point in time. Then this, at the end of the presentation, I'll be covering a little bit of housekeeping with that. Okay. The main, identical CAN IDs is the best problem you can have because that's really quick to fix. Bad CAN wiring sucks because if you've ever wired a CAN bus before, most teams wire it in what we call a daisy chain sort of configuration, akin to Christmas lights, right? Where everything is connected in series from one device to the next, to the next, to the next. And so if there's some bad wiring there, it can really give you a bad day. So I'm going to, well, first I'd like to ask, does anyone know some common causes for bad CAN wiring? Hopefully we can get some answers. And I'm actually going to stop share because I'm going to share something else. So while I'm resharing, if anyone wants to let us know, otherwise I will just share what I want to share. Okay. Well, it sounds like we have no takers. That's fine. Okay.
Oh, sorry, I was muted.
Okay.
Leon has his hand up. Feel free to unmute or type in chat,
Leon,
whatever
do you want to unmute or you want to?
Milan and I have a reason why CAN wiring can be bad. It is if we do not complete the daisy chain.
Okay, yep, that's good.
Work.
That's good. So you don't have, for example, two terminating resistors in your CAN bus. So one end of the bus is incomplete. Yes, that's correct. Definitely. Okay, so hopefully everyone can see this. Now, big shout out when I was doing some, compilation of this webinar, I found, and I've seen this before, even before I was actually doing this putting together these resources, but Bread has this amazing, in 2024, electrical binder. This is like one of the best things I've ever seen. Best thing since sliced bread, if you will. So, and it's quite thorough. So I will be making sure to link this into the, into the notes. And I can't go through everything now. But if you just do a quick scroll through, they've labeled everything beautifully. They have their CAD, highlighted and everything. But there's a few things I wanted to take from this. One, you can see what we call these one-line diagrams, if you will. And it gives you at a top glance, top-down view sort of, like really good way to see, okay, what's the order that these devices are connected, what's their IDs, so on and so forth. And what might be confusing to to FRC students is Bread is actually using a somewhat different topology compared to what most FRC teams use. So they're using one continuous yellow and green wire pair for their CAN bus, and then they're what we call they are sort of breaking out stubs. So most teams do what we call the daisy chain, right? Connect one device to the next to the next. That's perfectly valid. There's another way of doing it where as long as you keep, hopefully you can see my cursor here. This is what we call a stub. And if you keep this stub length short, it will work. But I won't go too on about that because it's actually a bit more advanced. But what I wanted to note from here is we have, as you can see here, we have one term. This is the 120 ohm terminating resistor that you have to have on one end of your bus. And in the other end of the bus, in the Canivore in this case, the Canivore has a built-in 120 ohm terminating resistor. So between both ends of the CAN bus, the Canivore up here and the terminating resistor here, they have the 120 ohms termination on both ends. This is vital for a CAN bus. With a tiny CAN bus, like one device CAN bus, you could get away with not having both. But with a CAN bus that's spanning the entire robot, you need to have both terminating resistors. Now, what I wanted to highlight is this TP here. Any ideas what TP stands for? Not toilet paper. Wait, maybe 5 more seconds. See if anyone can come up with it while I scroll down in this document. No. Okay. TP stands for test point. Test point. So what's really cool is they've actually sort of created, and they obviously had a lot of forethought into this of, okay, where can we put these test points? They've put these test points in their wiring such that they can probe with the multimeter, and when the robot is off, measure the resistance. Because if you measure the resistance at certain points in your CAN bus, it will tell you what's wrong. And there's a video that Bread linked. It's about a 15-minute video that goes through how to use the multimeter for all these circumstances. Once again, I'll be linking that. I would really recommend you watch it. But to summarize 2 of the quick ways to sort of do it, let's say I put my multimeter into this test point. I should be measuring 60 ohms. And you might be thinking, well, didn't you just say 120 ohms like 2 minutes ago? Well, there's 2 60 ohm resistors. And if you know how to combine resistors in parallel, if you have 2 resistors of the same value, then you just divide by 2. So since we have 2 120 ohm resistors in our CAN bus and they're connected in parallel, the resistance we should measure is 60 ohms. I see questions come up. Will it be more resilient if we run 2 CAN bus instead of 1? How many devices can 1 CAN bus carry at most? If one of the device, okay, these are some really gold quality questions. So I appreciate them being asked. So we'll go one by one. Many teams, as you can see, Bread has done this. They run 2 CAN buses. So they run what we call Canivore CAN bus, and most teams will put their drive components on that. Because if you're using all C2RE devices with your Canivore CAN bus, it actually runs at a faster refresh rate, if you will. So that can help you with stuff like gyro drift and whatnot. But also, it means that, let's say, your elevator snaps off the robot. It's really bad, right? But at least you'll maintain your drive, which is quite important in FRC. Because, look, mechanism is important too, but at the end of the day, you always want to be able to drive, right? So if you have your drive CAN bus as a separate one from your mechanisms, you're getting a little bit of redundancy in that sense. So that's that. Hopefully that answers question 1. Question 2 is an interesting question. Now, the Canivore CAN bus that I made reference to, that is using a protocol called CAN-FD, which is faster than the CAN bus protocol that the RoboRio CAN bus uses, which is just your standard CAN 2.0B, I think it is. So if you use a Canivore CAN bus, you can have more devices on the bus operating at faster speeds. But what the good thing is let's say you have 2 CAN buses anyways. Well, you've just sort of doubled your bandwidth because you've half the devices on each bus, right? So your CAN bus utilization will go down on each bus, if that makes sense. So there, and to sort of answer the question, because the question was how many devices can one CAN bus have? There's no hard fast rule, especially because it depends on your vendors. So mixing CTRE devices with Rev and so on and so forth, there's a lot of different variables at play. What is good though is that if you open up Driver Station, on the bottom left, there's a little lightning bolt icon. If you click that, it will show you what your CAN utilization is. And if you read your Driver Station logs, which we'll go into towards the end of the presentation, you can also have a log of your CAN bus utilization. Ideally, I think most people say try to keep it below 80%, which makes sense, right? Okay, last question. If one of the devices on the CAN bus has quality problem, how to troubleshoot? Quality problem could mean a lot of different things, but that's why, for instance, these test points are in there, because that can help you sometimes. One easy way to tell is, and this is what we were doing at MRT with EMU, is we would check every single CAN device to see if it was powered on. So because if one CAN device is not powered on, this can cause issues. So we would check before every match, is every device powered on? And that tended to help us. And we caught a couple of times some devices that had gotten disconnected or something like that. Some people rely on the indicator lights on the motors. For example, the Kraken motors, they have those lights, the 2 lights that they blink green, orange, red, whatever. I would be really careful about that. I always advise to hook up directly to the robot and use Tuner or Rev Hardware Client to check your CAN devices. Don't go based off of the lights, because people say, oh, the CAN bus is flashing red. It's flashing red. The Earth is ending, and they'll get so scared because their devices are flashing red. But there's many reasons why it could be flashing red, and you need the more verbose output that Tuner provides you. So I don't like to go based off of the LEDs for the CAN bus status personally, as a personal thing. So hopefully that answered your questions. Like I said, I'll make sure to include that CAN bus video. I actually have it open right here. It's a 18-minute video, and it is a really good video about how to troubleshoot with using a multimeter, not only resistance, but also using voltages and everything. It's really a good video. I liked it. So yes, this is what I wanted to highlight on the Bread electrical binder, their testing point. And also they have like these low power diagrams, which are quite nice too, that show how their power is connected. Of course, power is always going to be connected in parallel because we need the same voltage for our devices. We don't want different voltages based off of a series circuit. So that's sort of what we do. Cool. Okay, back to the presentation. Stop share and reshare. Okay, and we're hopefully back. Okay. Great. How are we doing for time? Okay. Well, good thing so yeah, bad CAN wiring. There's also a CTRE document that I'll be linking that has some tips on how to troubleshoot your CAN bus as well. So I'm not going to have exhaustive amount of time to cover it in depth, but if you read the resources, they're quite clear, and you can also send me an email. My email will be linked at the end. Some really good tips on how to troubleshoot your CAN bus. Okay. But there's one common thing I'd like to say. Many times I will check connections on the CAN bus, come to find out one connection, the yellow and the green have been reversed, right? Thankfully, it's not like power where you do that and it will fry or something. But if you do that, it will take your CAN bus offline. So this is another very common thing that happens. Somehow someone has connected yellow to green and green to yellow, and it takes your bus offline. Okay. Oddities with certain components. So Neo motors and SparkMax motor controllers from Rev. If you're using these, right, pair up your motors with your motor controllers. So pair up, okay, Neo A with SparkMax A, and so on and so forth. The reason why is because let's say you have a shorted motor, shorts somehow, don't have time to go over how this could happen, whatever, but we have a shorted motor or a shorted SparkMax. If you hook up the defective shorted component to a good component, it will fry that other component. I've had students replace like 3 Spark Maxes, for instance, of 3 Neos and fry each of them because they were hooking it up to a shorted component and it was frying the other one. So pair them together, swap them out as pairs. There's other actual diagnostic methods that you can do to ascertain which one is shorted. Once again, unfortunately, I don't have time to go through. But pair them up. That way, at least you're not frying, especially the Spark Max, because that's $90 US each time. Pair them together. Neo 550 motors. Some teams use these. We use these on our Swerve drive. Never, ever, 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 if you want the Neo not to smoke, exceed 30 amps supply current limit. If anything, you should go 20 amps. 30 amps is really pushing it. Pushing it is being generous. I would recommend 20 amps. These motors are very small. They don't have a lot of thermal mass, and the temperature sensor on them is placed in such a position that it will only detect that it is overheated too late once it's already melted. So really do not run above 20 amps. If you even want, you can actually swap out on your PDP from a 40 amp circuit breaker to a 20 amp circuit breaker. So you don't even need to do it in software. It's better to do it in software though, because that way there's less chance of the motor controller going offline if the breaker opens. Even though it's a thermal breaker, but you don't want an intermittent connection through there. So it's always better to set a software current limit, but you can even downsize your breaker as well to ensure that there's no chance it can go above 20, 30 amps. Kraken power pole adapters. Many teams are using the power pole adapter board on the Krakens. And I've seen many instances where, for example, the top Weidmuller connections, or however you pronounce that, for the CAN, they can get crushed, and then your CAN bus will be, disconnected because of that. So look out for that. And then this one is really, really important. To be honest with you, if you take anything away from this presentation, take this link away from the presentation. It's actually so important. I'm going to share this slide, share this link right now. Like, if you do not have this component on your robot, you need to buy it and put it onto your RoboRio. Basically, it's a much better connector for your power on the RoboRio. It allows a lot more conductor to be inserted into it, and that way it makes a lot better of a connection, and it's less likely that your RoboRio will disconnect, even under heavy defense, anything like that. It's really, really important, that connector. So in 2023, we weren't running with that connector. When we swapped finally to that connector, it solved our problems when we went over the cable protector on the field and we didn't disconnect anymore. Okay, sharing back again. Okay. Last thing I want to say is if you're using Rev motors, because Neo motors, I should say, they have the separate encoder cable coming off of them, which is required because they're a brushless motor. Be very careful. Those are very finicky. They're very thin, and they're using JST connectors, which can have issues with them. So be very careful with those because you don't want your $40 motor to be trashed just because of a bad encoder cable. Okay, driver station issues, and thankfully this sort of second half of the presentation a lot quicker, so we'll be able to get through it in time. Driver station issues, there's 3 of them that I noted. There's something called the emergency stop glitch. Basically, you can use the space button on your driver station to e-stop your robot. But sometimes, let's say your programmer was doing some, what happened? Is this still sharing my screen? Yeah, hopefully. Sometimes, let's say your programmer has been programming and they use the space bar, of course, during programming.
It's not screen sharing, by the way.
Oh, it's not screen sharing anymore? Okay, that's weird. One moment. Try this again. While I'm figuring that out. So sometimes they will, what's happened to my computer? Okay, from current slide. Okay, Alt Tab has stopped working. Let's restart this. Okay, we're back. Or we're not back with the screen share yet. Okay, sorry about that. Okay. So what was I saying? So yeah, sometimes you've used the space bar and you go into enable your robot and then it will disable quite quickly because it's registered, even while your robot was disabled, it registered the spacebar click. And then for whatever reason, it's some sort of weird glitch. I'm not a programming person, so don't ask me about it, but it will then e-stop your robot either during a match or even while you're practicing, and can be quite annoying. So way to fix, just restart driver station every match. Every match you go up to during queuing, just restart it. Even maybe not a bad idea to restart your laptop. Controller connection and assignment. This is a really bad one. There was one match I saw that I was actually the drive coach, and the controller was not connected and assigned properly. And because of that, the robot was working fine, but the drivers were trying to drive. In driver station, the connection between the controller mapping to the code was sort of incorrect. And until we did a rescan during the match to rescan and bring those controllers actually connected to the driver station, we basically sat there for a minute not moving at all. So this is something to check as well. You can go into the controller tab on driver station and check and move, for example, your Xbox controller and see, okay, controller number 0, it's this controller that I'm holding in my hand, that goes to the driver. Click on controller 1, it's this controller, it's connected, give it to the operator. Do that every match as well. Last thing, Wi-Fi in the driver station laptop should always be disabled when you get to the field. Sorry, Ian, I'll apologize in advance to the FTAs for sometimes it's not being the case. So what I would recommend when you're queuing, just make sure, do a double check during queuing that your Wi-Fi has been turned off, because otherwise the FMS, there's some issues with the connection between your driver station and the FMS if you keep the Wi-Fi enabled. Okay, radio issues mainly stem with, once again, with this new black radio, mainly stem from poor placement. So there's two things to consider. The backing surface of the radio needs to be chosen as metal. This is because the metal backing surface will act as a heat sink. I've seen it happen. The radio gets too hot. Let's say it's mounted against wood or something, and then now there will be a lot of latency that's introduced between your robot and the field because it's overheating and it needs to throttle the connection. The second thing is that the radio should be placed such that it's visible from afar and its lights are visible from afar, so the field staff can actually see what's happening with your radio lights. But also, that will help you if you place it on the outside of your robot and as far high as possible to get the best reception to the field radio, a field access point as well. Because if you bury the radio inside of your robot, the connection will be not as good. You need a line of sight between your radio and the field access point. So don't nestle the radio inside of the robot. It will be very bad for the connection. Transport issues, I sort of touched on this. Watch for crushed connectors. So let's say you have a robot cart. Some people have connectors that, for instance, are on the belly pan or bottom of your robot. And let's say you put it on that robot cart and it crushes the connector. This is something to watch out for when you're transporting your robot. Things to bring to competition, this is just something I threw in, spare fuses, breakers, prefabricated cables, crimps, maybe a spare motor, stuff like that. So over time, you will build up your list of, okay, what spare things we need to bring, but these are things that you should definitely have, what your team is actually using. Don't rely on the spare parts at the event, to be honest with you. This one's really brief. To use the driver station to your advantage, you learn how to read the driver station logs. Even without more advanced tools like Advantage Kit or Advantage Scope, the driver station logs have really good information, mainly pertaining to the electrical status of your robots. Okay. Receiving new components. I think this is my last slide, or one of the last. So when you receive new batteries, you should serialize the batteries with a label that contains, for instance, a serial number and when you introduce the battery into service, right? And you should also perform an initial discharge and internal resistance test with a tool like the CBA, Computerized Battery Analyzer. This will tell you very quickly if there's any issues, right? Let's say the capacity is way less than it should be, then you can instantly know that that battery is a bad battery, not to use it. And for example, if the internal resistance is much higher than it should be, once again, same thing. Also, a lead acid battery is made up of 6 cells, which are nominally 2 volts each. So let's say you're measuring 10 volts when you get the battery, one of those cells has been disconnected or something like that. So that's another thing you can check when you're getting the battery at the beginning. And the good thing is when you run this initial test, you can save the results and use it as a reference between the next test that you do after maybe your first competition or something. So you can see how the battery's health is going over the months. When you get new motors, motor controllers, please connect the motor/motor controller, whatever, individually to the RoboRio and test it individually. That way, you know, this motor is actually good, because many times, you get a, bad motor, unfortunately, you put it in thinking it's good, and then it takes forever to troubleshoot and find out that motor is not good because you didn't test it individually at the beginning when you received it. Okay, and last thing to end off with before I open to questions. Sorry for running a bit over time. But I sort of suspected this might happen, is general design advice for electrical. So we want to run wires such that they don't make loops that are catchable outside the robot perimeter, right? So you don't want a big wire loop dangling out of your robot, just asking for someone to come and rip out. It's really not what you want. So this includes energy chains and cable runs and all of this stuff. Keep it inside of your robot perimeter, please. Tie wires down, once again, so that they will not get caught by other robots or even by your own robot, maybe a mechanism inside or a game piece inside of your robot. This includes the battery cable once again. And there's one student on here, I won't name who it is, during MRT, hooked up the battery connection above our energy chain. So as the first time we tried to send up our elevator and the E-chain came up, it disconnected the battery. It was quite funny, to be honest with you. And he will never do that again because he learned not to connect the battery cable above your E-chain. But this is things to consider, right? Where's your battery cable going? So that way we don't have issues like that. The last thing, please, what I wanted to say is electrical always gets left last for some reason in FRC. Take a proactive approach to designing your electrical and your wiring routes and all these things with your design team. That way, it will pay you dividends at the end when your robot's actually working, right? So take a proactive approach, plan out the electrical, think about where things are going to go, and it will make your life a lot easier. Okay, please do not hesitate to email me. My email's here. Please email me with feedback about my presentation, content, style, and delivery. I'd love to hear it. And with anything I've covered, and I'll now open to questions and answers, hopefully.
All right, I'm going to stop the recording there.